Hello IP physics students, welcome to this next video. It is about momentum, impulse, and collisions. And it's going to be a pretty short pretty short video. We're just going to quickly go over some review of the material and then do 6 practice problems. So let's start with what is momentum. Momentum is just a quantity, a vector quantity that represents both the an object's mass and its velocity. So it's written with a p, even though there's no p in the word momentum. P is equal to m times v. In this case, m is a scalar, v is a vector, and so p is going to be a vector as well. Its direction is going to be the same direction as the velocity, which is nice. And one thing to note about momentum, Newton's second law actually applies to momentum. Originally, what Newton wrote was not that F equals ma, but rather the net force is going to be equal to the derivative of momentum with respect to time. Not F equals ma, but rather F is equal to the derivative of momentum. And why does this work? Well, if you take the derivative of momentum with respect to time, that's just equal to the derivative of momentum times velocity with respect to time. We know that mass doesn't usually change with time. In some scenarios, like in rocket propulsion, that's a famous example, mass does change with time because you use up more fuel as you go on. But in most cases, mass is constant. That's why it's a scalar. And so you can just take the m out and it becomes dv dt. And the derivative of velocity, as we know, is mass times acceleration. And so you don't really need to know this part or how to derive what we know as Newton's second law from this, but you should know this part. And yeah, that's basically all you need to know about momentum specifically. But we move on to our second concept, impulse, which is basically just the change in momentum. And no, it's not the change in momentum with respect to time. It's not the derivative of momentum. We know that is force. Instead, the impulse, which is written with a J, again, no J in impulse, just that is the letter given to it. It's equal to just the change in momentum, pure change in momentum, P2 minus P1. And so what else is impulse equal to? If it's only equal to this, it must have some other purpose, right? Well, the impulse is actually going to be equal to the net force times the change in time. And so that's one useful fact, because now we know we can just equate these two things. The change in momentum is equal to the net force times the change in time. And so that's going to be one of the biggest equations that you need to know for this unit, because it's going to come up in a bunch of collisions and example problems. If the force is changing over time, which it usually is in these kind of cases, then you can rewrite it using an integral, because this is a calculus level class. And so you write the impulse is equal to the integral from t1 to t2 of the net force dt. And so that should look pretty familiar to you. We've done stuff like this before, especially with like velocity, acceleration, things like that. And also work. Work is equal to force times distance. And since force could change, we write as an integral. And this is just the same thing here. So if you want the new equation, it would be the change in momentum is going to be equal to the integral from t1 to t2 of the net force dt. So yeah, you should probably know this top one, and then you can derive the bottom one from it if it's a changing force, because you should know that summation and integrals are basically interchangeable when it comes to the calculus aspect of it. So that's impulse. And one of our last topics actually for this unit is the conservation of momentum. And then the final topic is, of course, applying it to collisions, which is the third main thing in this unit. So what is the conservation of momentum? We've dealt with the conservation of energy, mass, all that before. This is no different. It's just saying that if you have a net external force of 0, so an external force is just a force that is not part of the system. It's exerted by something outside the system. So if there is no net external force, if is equal to 0, then the momentum is constant. That's basically what the conservation of momentum is saying. The momentum is equal to the first object's momentum plus the second object's momentum plus dot 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 all the way to all the objects that are in the system. It's also important to note that this is the vector sum, not the scalar sum. So if you have this and this, those momentums are going to cancel each other out. You can have two objects that are moving, just like not at rest, completely moving, yet the net momentum is zero. This is going to be occurring in some of the collisions we look at, where they're moving towards each other with the same speed and they have the same mass, and so the net momentum is zero. It's they're just going to bounce each other and go the same opposite directions with the same speed, or they would stick together and stay at rest. But yeah, you could have a net momentum of zero with its components being non-zero. And if you have a system that's broken down into subsystems, each component of that total momentum is also separately conserved if there's no forces acting between those subsystems. Now that we went through that, our last topic for this unit is collisions. There are two main types of collisions, elastic and inelastic. So when you have an elastic collision, both the kinetic energy is conserved, basically. You have, let's say, these two balls, one going towards the other slowly moving away. This one's going to catch up to it and collide with it and probably get repelled back here. This one is going to go even faster forward. Now, this is if this was an elastic collision, that means not only is momentum conserved, momentum is always conserved in collisions, no matter if it's elastic or inelastic, kinetic energy would also be conserved. And so you could be given less information to begin with, and you can find out a lot more because you have a system of equations now. Not only is this constant, you can write it as constant, or you can write it as P1 is equal to P2, or Pi is equal to P final. You also have Ki is equal to K final. And so now, if you have mass and velocity as the two unknowns, you have a system of equations, so you can deal with two unknowns. If it was inelastic, that means that kinetic energy is not conserved. And so you do not know this. But we do know that energy has to be conserved. So when can kinetic energy not be conserved? For example, if there's friction, it can slow down. Or the most common example, if it's completely inelastic, they stick together. And this is if the two bodies have the same final velocity. They just stick together and they move as one. That means kinetic energy is lost a bit there, but momentum is still conserved. So you can solve for some stuff there. And yeah, that's basically it. Just know the difference between elastic, inelastic. You should be able to identify when collision is elastic or inelastic. It usually tells you, but sometimes you have to infer based on the context. And then, yeah, you should be able to solve for the mass, velocity, all that using the conservation of momentum, and if it applies, the conservation of kinetic energy. So yeah, let us move on to the 6 practice problems that we have today. Okay, first one here. This is just a simple problem about impulse and momentum. It basically says you have a hockey puck moving on icy, frictionless horizontal surface. That's always good to know. That means friction is not, there is no net external force. Friction would have been an external force. In this case, there is none. At t equals 0, the puck is moving to the right at 3 meters per second. So v initial is equal to 3 meters per second. You should write the sig figs and the units, but since this is just a brief explanation of how to solve it, I'm going to ignore it for now. We also know that the mass is 0.16. It says calculate the velocity of the puck, magnitude, and direction after a force of 25 newtons. Is directed to the right, and it's been applied for 0.05 seconds. Okay, so what equation are we going to use here? Well, in this case, the force isn't changing, so we can just use the change in momentum is going to be equal to the net force times delta t. Right. And so what is the change in momentum? That's just m times v final minus v initial is equal to, in this case, there's only one force times delta t. Okay, mass, we know, we could plug in stuff right now, or we could just move everything to one side. I'm going to move everything to one side because that's usually how we like to solve problems in AP Physics. You can divide by m. You're going to get this. And then you just have to add VI to both sides. And you're going to get this. We wanted the final velocity, yes? So let's assume right is positive. That means this is indeed a positive velocity. And the force is also positive because it's 25 newtons directed to the right. And so you just plug stuff in, right? You plug in 25 for F. You plug in 0.05 for T. You plug in 0.16 for M. And you plug in 3 for VI. And then you just solve for V final. And you're going to get 10.8 meters per second to the right. It also asks for the direction, so you just have to denote if it's left or right. Since the velocity initial was to the right and the force was to the right, it would obviously be to the right in the end. Okay, the second part says if instead a force of 12 newtons directed to the left is applied from t equals 0 to t equals 0.05. Okay, so we can use actually the exact same formula. We just have to plug in different stuff. In this case, force would be negative 12. And that's because it's a force to the left. Time would be the same, mass would be the same, and initial velocity would be the same. But if you were to solve for it, you would get actually a negative velocity, negative 0.75 meters per second. And what that means is it's going to be going to the left. The force was enough to actually change the direction of the puck. Yeah. All right, so that was our first problem right here. Second one is a graphical problem. And one thing I didn't mention, but we've covered it in previous units, is that the integral is just the area under the curve. And so every time you see an integral in an equation or in a concept, right, an integral relating to things, you can do it graphically. And so that's why I included this problem. You have a graph of force versus time. And so the impulse, we know, is going to be equal to the integral of force with respect to time, which means that the impulse is just going to be the area under this curve. That means the change in momentum is going to be the area under that curve, and so on and so forth. Okay, with that out of the way, let's look at the problem. The mass here is 2 kilograms, is sliding to the right, frictionless, good. VI is equal to 5, and we're assuming right is positive. It's struck by an object that exerts a large horizontal force on it for a short period of time. The graph shows the magnitude as a function of time. What impulse does this force generate on the stone? So, for only 1 second, for only 1 millisecond, be careful of the units. That's milliseconds here and kilonewtons there. Okay, so for only 1 millisecond does the force occur, and it's 2.5 kilonewtons, so that's going to be 2,500 newtons for 0.001 seconds, right? Always try to come back to the base units. So you're looking for the impulse. Well, that's just going to be the area under the curve, and so you just find the area, right? And this is just a rectangle. It's nice and easy. No integrals required, or no complex integrals required. So this is just 1 times 2.5. Don't forget the units though. The kilo and the milli actually cancel each other out, which is nice. And so you just have to multiply length times width. That's 2.5 times 1, or 2.5. And so your impulse is going to be equal to 2.5. Now, what is the units for impulse? It's going to be equal to newtons times seconds, because that's literally what it is. Newtons times seconds. It could also be something else like usually it's just going to be that, but kilogram times meters per second is also a unit. That's usually used for momentum, and since impulse is the change in momentum, it can have the same unit, but it's more common to write as newtons times seconds, because that kind of reminds us of the formula: impulse is equal to the force times the change in time. So your impulse is just going to be 2.5 newtons times seconds. Just after the force stops acting, find the magnitude and direction of the stone's velocity if the force acts to the right or to the left. So if it's acting to the right, that means this is the impulse, 2.5 newtons times seconds. And so you know that the impulse is equal to the change in momentum, which is just m times v final minus v initial. So we can use a very similar formula as last time, where we just divide by m and then add vi to both sides. So v final is going to be equal to j over m plus v initial. Okay, so now we can just plug stuff in. J is 2.5, m is 2, vi is 5. And so since velocity is to the right, force is also to the right, you just add them up. V final is going to be equal to 6.25 meters per second to the right. Okay, what about if the force was initially to the left? That means impulse would actually be negative 2.5, so you would have to factor that in. Use the same exact equation. V final is equal to negative 2.5 over 2 plus 5. That's actually going to be negative 3, not negative, positive 3.75 meters per second, still to the right. So even though the force was to the left, it's still not enough to change the direction of the velocity like it did in the first problem. So yeah, that's going to be your answer. All right, third problem here. You got astronaut doing repair on the space station. She throws 2.25 kilogram tool away from her at 3.2 meters per second relative to the space station. With what speed and in what direction will she begin to move? So this is kind of like a collision problem. It's usually referred to as an explosion problem, which is the reverse of a collision. Things break apart or move away from each other instead of colliding with each other. It's not always an explosion. In this case, it's not the colloquial definition of explosion where something just blows up. It's just, something that was together is now not together. And so you still use very similar things as to collisions. You just use a conservation of momentum. And in this case, we know the two masses and one of the velocities, and so we can just figure out the other velocity very easily with a simple conservation of momentum. P1 is equal to P2. Now in P1, it's going to be 0 because they both are just at rest in space. And then so P2 also has to be 0. Now, how does that work if one of them has a velocity? Like I mentioned before, you could have 0 momentum with non-zero components. And so you can just write P2 is going to be equal to, let's just call it PA for the astronaut and PT for the tool. PA for the astronaut is M times V astronaut plus, or M astronaut times V astronaut plus M tool times V tool. And we know that's going to be equal to 0 because of our conservation of momentum. Let's see, what do we know? We know mass of the astronaut is 68.5 kilograms. We know mass of the tool is 2.25 kilograms, and velocity of the tool is 3.2. It doesn't say what direction it is, but we need to know what direction she will move. Instead of saying right or left, we can just say direction is opposite to the direction as which she throws the tool, because they can't possibly move in the same direction. That means the momentums won't cancel out. So we do know that our velocity is going to be negative. We can just write it as a negative answer. So you just solve for v. It's a simple linear equation. You do the calculations, move stuff to the other side, and divide by the mass. You're going to get a VA of negative 0.105 meters per second. And that's your answer. The negative just indicates that she's moving the opposite direction. All right. Moving on. That was a relatively simple collision problem. Some of these other ones are going to be a bit more difficult, but it's still the same underlying principle. On this one, it says frictionless. We love frictionless stuff. This is not like real life, but we love frictionless stuff. Just makes our life easier. Okay, we got a puck with mass 0.25 kilograms moving towards another puck with mass 0.35 kilograms. So A, B, slightly bigger. Initially at rest. So this one is just now moving, but this one is moving with a velocity that we actually don't know. That's what we're trying to find out. After the collision, puck A has a velocity of 0.12 meters per second to the left, and puck B has a velocity of 0.650 meters per second to the right. Okay, very similar to the previous one, where we have momentum initial plus momentum initial is equal to momentum final, which you can write as 1 and 2. And so that's just going to be MAVA plus MBVB, both initial, is equal to MAVA plus MBVB. I did not have space for that. I should have planned better. All of these are going to be finals. And so one thing we know, this is 0. The velocity of B initially is 0, and so this entire term is 0. That's one thing we can cancel out. What else can we do? Well, not much actually. We can just solve for VAI. That's what we want to solve for. And so you just have MAF VAF plus MBF. Again, did not plan this out very well. VBF over MAI. So that's a very simple formula. Just plug everything in. We know all of this. MAF and MAI are the same thing. We know MBF. That's just the masses. VAF and VBF, they give it to us. So we just plug in all of those values, and we're going to get a VAI of 0.790 meters per second. And that kind of makes sense. You can just make sure that like the answer is in the realm of possibility. Otherwise, you probably did something wrong. And the second part of the question says calculate the total change in the kinetic energy of the system that occurs during the collision. So that means this one is going to be inelastic, which kind of makes sense. If it was elastic, it would have said so. But we want to see exactly how much kinetic energy is lost. We know kinetic energy is lost, but how much? So let's calculate the initial kinetic energy. That's going to be equal to 1/2 MAI times VAI squared. I'm ignoring the vector sign for now because we just want the magnitude. Kinetic energy is a scalar quantity. And then we also have to add the MBI VBI squared. Okay, we actually know all this. This is 0. Good to know. And for MAI, we know that's 0.25. VAI, that's 0.790. We just found that out. And so you can find it, you can multiply them, square it, you get 0.078 joules. Okay, what about the final kinetic energy? That's going to be equal to, again, 1/2 MA final, VA final squared, plus 1/2 MB final, VB final squared. Again, I mean, in this case, we cannot cancel anything out. We can just plug stuff in. We know the two masses. Velocity of A final was negative 0.120, but since we're squaring it, the negative sign doesn't matter. And then for final B velocity, that is going to be 0.650 meters per second. And so you just add all that up, and you're going to get 0.0757 joules as our final kinetic energy. And there is a difference. It's just the change in kinetic energy. It's going to be K final minus K initial, and that's going to be negative 0.0023 joules. So a very small change, but if you look at the actual values, it is a pretty significant change. You can find the percent, but they're not asking us to, so why bother? That's just the change in kinetic energy. All right. Almost done. We just have 2 problems left. Number 5 here. We got a football field. I don't know why it says very muddy. They don't even give us anything about friction, so who knows. But there's a 110 kilogram linebacker. So we got an L, and we got a halfback, H. Let's see. Immediately before the collision, the linebacker is slipping with a velocity of 8.8 meters per second north. 8.8 meters per second north. And the halfback is sliding with the velocity of 7.2 meters per second east. So 7.2 meters per second east. What is the velocity, magnitude, and direction at which the two players move together immediately after the collision? So they're going to collide and stay together and moves probably somewhere in this direction. We want to know the magnitude and direction. So this is going to be one of the ones where we actually have to use vectors. So we have to find the components and then find the magnitude and direction from there. This one's not going to be that bad because we have the conservation of momentum, right? And so we have ml times vl plus mh times vh is going to be equal to together times v together. That's just our equation. We know the masses. That's going to be 110. This is going to be 85. We also know the velocities, but we can't just scalar multiply we use scalar multiplication, but we can't just add them as scalars. We have to add them as vectors. And so if you what's nice about this is it's completely north and completely east. So this is just going to be 8.8 j hat because it's the vertical vector, and this is going to be 7.2 I hat because it's the horizontal vector, and they both are in the same direction. We don't need a negative sign in here. So if you were to multiply it out, you would get the linebacker is the one moving north. So 8.8 times 110, that's just going to be 968 j hat, sorry. Yeah, j hat. And then 85 times 7.2, and this is going to be I hat. So in this case, we actually don't need to add them together. It's going to be 612 I hat, right? We can't just add those together. That's going to be the complete vector. And now we just need to divide it by the total mass of the linebacker and the halfback. So that's going to be divide by, so it's 110 plus 85. So that's going to be 3.14 I hat. And if you were to do j hat, it's going to be very similar, 968. So it's just going to be 4.96 j hat. And so in the north direction, the total velocity is 4.96. In this east direction, it's 3.14. And so those are the components. To get the magnitude, we just do square root of 3.14 squared plus 4.96 squared. And if you were to solve for that, you would get 5.9 meters per second. So that's the total velocity. Now, what direction? Well, that's where the formula for direction comes in. It's inverse tangent of the two components. So it's going to be the y component over the x component. And solving for that, you're going to get 58 degrees. And just make sure, 58 degrees. And just make sure that's the right quadrant. As we can see, we were predicted they would go in this direction after they collided. And 58 degrees does make sense. If it was like 180 plus 58, it would be somewhere there, which they're not going. It's just in the first quadrant. So that's our answer, 5.9 meters per second and 58 degrees. All right, last problem here. So there's a particle accelerator. You have protons of mass m, and you have the speed is 1.5 times 10 to the power of 7. And then there's an unknown element. You just have a nucleus. Let's see. After they hit the nucleus, these guys come back with a smaller speed, 1.2 times 10 to the power of 7 meters per second. They rebound, so they're going the opposite direction. So let's just say this is negative speed. If the initial speed of the target nucleus is negligible, so just count to 0, the collision is elastic. That's important. Now, there's a few things we don't know, namely the mass of the proton, and, well, technically we do know the mass of the proton, m. We're just using it as a base. We don't know the mass of the nucleus, and we also don't know the final speed of the nucleus. And so that's where the system of equations comes in handy, where you have both conservation of momentum and conservation of kinetic energy. That's going to allow us to solve for two variables, which we have to do in this case. So it's a good thing they told us that the collision is elastic. We couldn't have solved the other. So first things first, let's write out the momentum equation. We have m proton, v proton, plus m nucleus v nucleus is equal to m proton v proton plus m nucleus v nucleus. And then just final, initial. Okay, we said that was negligible, so we can get rid of it. Now, let's simplify things a bit. We know that m proton is just m. And VPI, we know, but I'm just going to leave it as VPI. And that's going to be equal to MPF is still M, and then VPF plus MN, I'm going to leave it as MN because the final doesn't matter, times VNF. Okay, that's one equation. The other equation is the kinetic energy equation, where we have kinetic energy initial is equal to kinetic energy final. So that means 1/2 MPI VPI squared plus 1/2 MNI VNI squared is equal to 1/2 PF VPF squared plus 1/2 MNF VNF squared. Again, this is negligible. We can get rid of that. And simplifying it a bit, 1/2 M VPI squared is equal to 1/2. Well, I can actually just get rid of the 1/2s because they're everywhere, so we can just divide everything by 1/2. So is equal to M times VPF squared plus MN times VNF squared. Okay, so those are our two equations here. Let's just circle them. And this is just a system of equations. You would want to plug in the numbers because otherwise it just looks like there's too many variables. But the only variables here are MN and VNF. You got MN, VNF, MN, VNF squared. And so one thing you could do is move this and this to the other side, divide both equations by each other, and just get VNF. So you can solve for the velocity. And I'm not going to show you how to do that because it's just algebra. But like I said, after you move it to these sides, all you'll have on each side is this and this. And so if you divide them, you'll be left with VNF on this side. And on the other side, you'll have some combination of numbers and variables. If you just turn the M's into, if you turn the velocities into the numbers, the only variable left is M. And in this case, the M's cancel off when you divide the equations. And so you're just going to get a VNF of 3 times 10 to the power of 6 meters per second. So, yeah, technically that was part B, but we found it first, so it doesn't matter. For the mass, then you just have to plug in this velocity back into this equation, for example, and everything else is a number except for M, which we leave as M, and we just solve for Mn. And if you were to solve for Mn, you would just get 9M. Very nice numbers here. So yeah, that would be your answer for this last problem here. Okay. And that's it for this unit, just momentum, impulse, and collisions. Technically, you could also have center of mass in here, and I don't have any practice problems for center of mass, but very quickly, what I can say is that center of mass would just be the integral of mass times the radius. So you would just do, technically it's r dr. But that just means position. And so if you weren't to use calculus, it would just be equal to the summation of each mass times each position as a vector divided by each mass. And so that's where this integral comes in. Usually you're not going to use this integral, but in some cases you're given a weird shape like a semicircle, and you would want to use the integral. You're not given like actual discrete particles, you're given a continuous shape. And so what you would do in that case is just, use the integral. This is a calculus-based course, so you should be able to do that. But in general, you would use this formula, where you just add up the, it's similar to momentum, but it's just mass times position. You add up all those and divide by this total mass, and you're going to get that. So yeah, that's technically it for this unit. Just briefly went over center of mass as well, but this unit's shorter than the others, and so just keep in mind the impulse force relation as well as conservation of momentum and the different types of collisions. Those are the three main things. So yeah, good luck for your test and the AP test.